So let's do a quick review of the quiz here. So when I put this together, I really tried to stick as closely to our notes and the roadmap, or rather the other way around. The roadmap was written in such a way that it corresponded pretty much directly to the actual test or quiz. And I believe for the multiple choice, single correct, and multiple correct, you will see the correct responses. So what I'd like you to do is just right now ask any questions that you might have, you know, why something's correct or not. Where we can go through these quickly. So the first one here, right, the three possible outcomes are, of course, success, failure, or error, right? So green, orange, or red. And there's another possible outcome. Can anyone think of any other possible behavior you might see in a test method other than success, failure, or error?
Ignore.
That's true. Ignore is another possibility if it's if a particular test method or class was marked as ignore because it maybe doesn't apply yet to your code, and you kind of flagged it as ignore, maybe using an annotation to that effect. So that's a good one. Any other possibilities when you're actually running the test, a particular method, anything other than success, failure, or error that you might observe? So let's think out of the box. In general, what are possible behaviors of a program? So it might terminate normally, right? It might crash. What else might it do? That's exactly right. So that might happen when you're testing also, right? So, I mean, that's of course something you wouldn't want to happen. So but it's something that wouldn't show up as an error because theoretically it's tied to the halting problem. That's just something that we see if it doesn't come back or if it's stuck in a test method, right? That's right. So non-termination might appear during testing. So you just the way you would see this is that when you're looking at it on your workstation, of course you will just wonder after half a minute or a minute, or depending on how big the test suite is, what's going on there. So let's say, oh well, that looks like it might be stuck in an infinite loop or so. So I better just interrupt it and then investigate, right? When it's happening in an automated, like one of those hosted build chains, like I have for some of my examples, right, where it builds on a continuous integration server like Travis CI or so. What you would usually have is some kind of timeout, right? It might time out after whatever 30 minutes or so, So you would get back an email message saying your build process has timed out. So that's kind of the equivalent in that kind of hosted context. All right, very good. So next question. There's only really one correct here, which is B, right? Because testability enables you to build confidence in the extent to which your system under test satisfies the functional requirements. If your system isn't testable, if it's not set up to be tested, then then your ways to verify or examine whether the system functions properly is much more limited, right? So you can just kind of try it out manually. So I always like to give examples from the embedded system space. So embedded means combination of software and hardware in such a way that there's a proper, let's say, function that comes out or value that arises from this combination. So one of my favorite examples is, of course, the vending machine, which has come up earlier, where I almost had this terrible fail, you know, and then I had to kind of shake it a little bit so that ultimately the outcome was as required, really. And another one that I really like is cars. And cars are designed to be testable as of, I think, the mid-90s. There is the so-called onboard diagnostic port, right? So is anyone familiar with this? OBD, exactly. So it's usually somewhere under the steering column. And you can then use a standardized testing device. You connect it, and then it can read the error codes. So that's just an example of a system that where there's kind of a universal standard for those systems to be testable. Okay, so that goes quite far, right? So we don't quite have that, but we have kind of architectural approaches. So what's standard is kind of the pattern of making the software modular so that you can invoke pieces of it and then look at their behaviors and test those systematically. Okay. It's not a standard pluggable interface, but it's really more of an approach where modularity, when done right, gives you testability. So you can think about it in the following kind of chain. So you want to make sure your system is correct, meaning it satisfies the functional requirements. That drives the need for testability, which gives you ways to verify this, not verification in the strict sense, but to build confidence, right? Because failed tests just tell you something's not correct, but to prove through testing that a system is correct, the testing would have to be completely exhaustive, which it usually isn't, but at least usually you achieve decent coverage. Okay. And the testability then, as the next step in this chain, benefits from proper modularity as we've seen. So that's really what Project 1A has been about, right? And the process tree example and the more recent and simpler iterators example. Okay. Testability cannot guarantee any of these other things, right? So, okay. Any questions about testability? And then this one was pretty much out of, and this is actually our connection, our plug-in point for Project 2A. This section 3.4 in the notes, right? This is pretty much out of that, and let's just go through these just to make sure we have complete agreement and clarity here. So, what is, let's see, so let's start with a tuple. How would you describe a tuple? So, for example, you could have an item that's a string, then combined with an int. So, are tuples homogeneous or heterogeneous? Heterogeneous, exactly. And once you create the tuple, what can you say about the length? So, for example, once you say, I'm going to have this tuple of the string hello and the number 3. Is the length, once you create it like that, is it fixed or variable? You cannot really add more items once it's fixed. Once that tuple, once you create that. But you're right in the sense that you decide.
Yeah, I missed that part.
Yeah, no, that's fine. It's all fine. I mean, once you decide what it should look like, so of course you have a lot of choices. So you can have an int combined with a string and combined with an array or whatever. So it's heterogeneous, and it's let's say it could have an arbitrary number of pieces. So it aggregates an arbitrary number of pieces, but once you create it, then that's what it looks like. So it's fixed, and that's why in this case, tuple would be a fixed length aggregation of heterogeneous items. So what about, let's see what's going on here. So sequences and lists. So we're familiar with ordinary mutable lists from our prior work in languages like Java, Python, and so on. So that would suggest A, right? So the items are all of the same type, at least at some level, right? So you just pick the most general type, and you say that's the item type. So for example, you might have a type vehicle, and then you might have car, motorcycle, and then you have a list of those different kinds of things in there, but the item type is the common general supertype vehicle, right? So in that sense, it's homogeneous, and the length is variable. So it can grow or shrink, so that would be that. So sequence or lists or queues, any of these kinds of linear collections are variable length aggregations of homogeneous items. And then parametric types, that's genericity, and that leaves, assuming there's no distractor in there, distractor item, that leaves variation or subtype polymorphism, like vehicle, car, motorcycle. That's the ability of a type to have multiple subtypes or implementation types, right? We're familiar with that. In 2A, we're going to revisit this, right? You're intimately familiar with the subtype polymorphism concept from intermediate OO. So the shapes example is a really good one, yes?
Could you reiterate what you said on number 3, genericity?
Yeah, so when you have a parametric type, so for example, a list of some item type, so you just define that list type, and the item type is a parameter, like a placeholder. Okay, just like methods can take parameters, so this is at the type level where types can take parameters. So where you say, I'm going to define this list or stack class once, leaving the item type T as a placeholder, right? And then if I need a stack of chairs, I say, okay, that type T becomes chair. So I get my stack of chairs. Or I can have a stack of books, so T becomes book, and then I have my stack of books, but using that same implementation code. Okay? Yeah.
What's the point of generics, though? Why the shorthand? Why would you want to do that?
Why you would want to do generics as opposed to what?
As opposed to not.
Okay. Because with generics, you need to define your stack code only once. And you're basically using that same code, and it applies to many different scenarios.
Okay.
Right? So it reduces code duplication quite dramatically, right? Because otherwise you'd have the same capabilities, so you'd have very similar or identical code to manage, let's say, a stack of chairs and a stack of books, right? And that's generally desirable to avoid code duplication for a number of reasons. I mean, one being, you need to test and maintain really only one code base as opposed to multiple, essentially, copies.
And is this limited to just like certain languages, or can you implement this in any language?
Okay, so that's a good question. So this is a language design choice. So there are languages that have it, there are others that don't have it in some form. So for example, and it's tied to a kind of more broad or overarching design choice, and I think that the corresponding picture, I think, appeared on the Slack channel recently. I'll have to double check. But there are languages that are statically typed, where you, for each variable or reference you declare, you need to specify what the type is. So for example, in Java, you have to say whether something's an int or a list of int or a list of string or whatever. So that's an example of a statically typed language where everything has every expression, every variable and every expression has a type. Then there are dynamically typed languages such as Python, JavaScript, etc., where only values have types as opposed to variables. Okay, so and typing plays a role at runtime. That's why they're called dynamically typed languages. So generics make sense only. It makes sense to talk about it only when you're on the statically typed side. Okay, so within the statically typed languages, so for example, C doesn't have generics, but C++ has generics in the form of templates. So you can parameterize classes in C++ and methods using templates. Okay, and in Java you have generics, which are kind of a more, let's say, a more foundationally well-defined mechanism for, and therefore simpler mechanism for achieving parameterized types, and Scala has a similar but more powerful genericity mechanism. Okay, so it's definitely very much tied to language design. Some languages support genericity or parametric types, others don't. Excellent. Other questions? Okay. So now part 2 is pretty much tied to the iterators example. So this was really meant to be just, I gotta silence this just a second. Okay. Meant to just reiterate, give you the opportunity to demonstrate your understanding of those examples and the project. All right, so let's look at this. So it defines those lines, then converts them to a list, and then prints each item in the list. Where do the items come from? Well, from the standard input, line by line, and then it prints how many lines have been counted. So that would be, really, this is of course only one correct, so it would be A. It echoes back each input line, and then prints the total number of input lines read. So strictly speaking, okay, it reads the lines and then echoes all of them back, and then prints out the total count, right? So what is wrong with this then? So what if you have a lot of lines? Can anyone think of any issues here? What if you have a lot of lines, like millions or gazillions?
Memory constraints, you're just putting them all into the list.
Right, exactly. The fact that you're converting the iterator into a list means you have to have memory for all of the lines. So now, normally stuff where you have large data would be on secondary storage, so disk space, whereas memory is your primary storage, and that's usually more constrained. Although with big data, machines, supercomputers have lots of memory now, and even ordinary computers have lots and lots more memory than they used to, but it could still be a constraint, and normally secondary memory is designed, because that has also grown, is designed to have much more capacity, right? So when we talk about RAM, we talk in terms of gigabytes usually, right? So now this is a 5-year-old machine and has 8 gigabytes. Then I have a Dell at home, a Dell laptop that has 16, and now you can get laptops with 32 gigs. But then disk, so that's primary memory, RAM, right? And then you have disk space that's now half a terabyte, multiple terabytes. So that's like a factor of about 1,000, right? Between 100 and 1,000, what you have in terms of primary memory versus secondary memory, right? So that is generally still an issue, even though RAM has grown a lot, typically. All right, so that's really the key issue. So this doesn't scale. It'll run out of memory on large inputs. That is one issue. What's the other issue here? So how would you test the fact that this program should behave like this? How do you test that? Well, you can test it manually or by scripting it outside of the program, so outside of code, using shell scripts or so. All right, well that makes automated unit testing less convenient than doing it JUnit style, where you write code in your same language or some other Java-based language or whatever to test different pieces of your code, right? You can only test the whole thing here because it's actually what you could call a monolith. I mean, it's very tiny for a monolith, but it is a monolith, so you can only test it externally, not different pieces of it. So the other items are not applicable really, because the fact that you're storing it in the list will not make it significantly slower, and then it's certainly very readable, so it's not complex or anything. Okay. So to make it better, you would have to first of all remove this invocation of toList. So look at the iterators example where we leave everything as an iterator, which means the idea is that you're only at any point in execution considering one input item. And that gives you the constant space performance that you want for these types of programs. Not all programs will have constant space, but the kind of program like a moving average or so, there it's actually critical for these kinds of long-running things that are supposed to process one item at a time. And it's not a matter of, so there are different dimensions here. So it's not a matter of velocity of the data. So even if you get only one reading an hour, right, if you let the program run for many months, you might still have a problem. A space problem. So the idea is just to say, okay, I'm going to take the most recent reading, process it, update the let's say moving average or other statistics or whatever I try to compute based on the most recent value or most recent n values, like in our moving average, and then update some kind of response, and then never consider that item again. Okay? So that gives you constant space, and that's highly important for these kinds of long-running systems. So, I mean, you wouldn't want a vending machine that somehow grows and grows, like as it sits there and performs its function, right? What is the vending machine's function? Well, in short, just sell you items and on demand. And then there's a kind of supporting function, which is if it has beverages, it's supposed to keep the beverages cold, typically, right? So that's kind of an additional requirement of a typical vending machine for beverages. But the vending machine has to operate in constant space. You cannot allow it to take successively larger footprints, as it sits there, which does not make sense. So you want to use those kinds of analogies and see if you can apply those to your software. So the same thing, the vending machine software analogy would be really more like an interactive game or something. So you want that to support longer sessions without causing your computer to run out of memory. So that's a more direct analogy. I mean, this is more for a kind of server process. All right, so, and then this one is pretty much straight from the notes also, and we've gone through this. I think most people got this one just fine. So in fact, all of these apply, right? We got the command line arguments for options that you set at startup of your system, meaning the software. And then it's got standard input, and it's got standard output and standard error. So these are the 4 ways. And then, of course, you can have additional ones like explicitly reading from or writing to a named file. But you only need that if you have more advanced requirements in terms of file I/O or so. And then there are other ways to communicate. So in your operating systems course, or probably in 264, you probably heard of a general class of mechanisms called IPC, inter-process communication. So these kinds of standard input and standard output, standard error are part of that. That's one way of having inter-process communication. Others are shared memory. There are named pipes. These are what we've seen are anonymous pipes, but you can also have named pipes, where then the pipe shows up like a file, but it's not really a file. Okay, so there are a bunch of mechanisms for that, but these are the kind of most basic and actually, in some sense, most useful ones, most widely used. Any remaining questions about this part? Yes?
Question 2, I believe, where we have to select the functional issues with the code. I was thrown off by the word function because all of those are non-functional requirements as listed in the text, so then I selected none of the above, because technically it would not impede the initial ability to carry out the requirements, but it would just be limited later on in the word.
Okay, let's see. Okay, I see. So that's definitely a valid consideration here in the following sense. So I would agree partially with your observation here. So in the following sense. When we look at non-functional requirements, we have dynamic ones and static ones. I agree that static non-functional requirements will not impede the ability of the software to function. Okay? They will, so for example, poor readability, that will impede the ability to maintain that software.
Correct, but it wouldn't mess up its function.
Right, but the scalability part will. So the dynamic functional requirements will actually get in the way. So if the function is echo back the lines and then output a count, and you blow the memory because it stores all the lines, then that's something that will actually interfere with the ability to function. So what I can do is, let's see. I can give you partial credit for let's say for the fact that I expected C to be checked, but you got a deduction for not checking it. Okay. All right, so see me after class, okay? And I will apply that uniformly to everybody. So I'll just regrade that. Okay. Does that make sense? So I'll take care of that. All right. Any other questions? I'll make sure to improve the wording for this type of question. Any other comments or questions? Okay. All right. And then 3, also very similar. So this is really about plugging these things together. So I'd like everybody who had some trouble with part 3 to look at this again in conjunction with process tree, the way process tree works, and the way iterator, the modular versions of the iterator works, and section 3.5 from the notes where we're discussing that. So let me just give a quick overview. So what does this actually do? Okay. So it takes this iterator of strings, and then it keeps going, right? So it says, okay, let's see if there are any items. If there is one, we'll retrieve it and add it to the output queue. Then we check if there's another one. And if so, we just retrieve it and advance the position of the iterator without adding it. And then we repeat that, right? So how does that behave, right? So it'll skip every other one. So it would be skip every other item in the iterator. Does that make sense? So that's a very important capability, just to look at code and make sense of it. And it's just kind of a mindset or habit of being able to trace through different executions mentally or on paper, based on the code and different sets of, or different arguments, in this case, different iterators. All right. Now, so the terminology from section 3.5. So what role does mystery main play? So is it a pure interface that says, okay, there has to be this method or this set of methods? No, there is actual implementation stuff there, right? So that eliminates that. Is it a concrete main program? No, because it's still a trait, so that means it's too abstract to be a main. Okay. So clearly it provides some implementation. So it definitely has some kind of provider role, right? Does it have any other roles? Well, let's look. Is there anything that is in there that it doesn't have, that it needs to receive from elsewhere? Any thoughts? What is it missing before we can just say, object my main extends mystery main? Because that would give us the concrete main that we can run, because it extends app. But what is mystery main relying on that it doesn't already have? Say it loud. Okay. I hear some people thinking out aloud, but if you know it, say it. So clearly let's look line by line, right? So that get lines, that's a library method, right? So that's there. Println is also a library method, that's there. So let's look at the line in the middle. What does it rely on? The run method. Where is it? It's not there, right? So that's a hole that needs to be filled, right? So in that sense, mystery main is a client of some other component that would actually provide the run method. So the common contract is this mystery. This is a contract. So this just defines the run method, or declares the run method without implementing it. So in that sense, it's a template method. That's what it's called in patterns terminology, right? So mystery main says, I am a client. I'm entering the contract mystery that involves the run method as a client, because I'm using it but not providing it. And the corresponding provider of the run method is mystery impl, of course, right? So mystery impl is purely a provider, and that extends report stuff there that must have been left over from, I guess, some earlier version or so. So that was, that shouldn't have been there, but it really didn't interfere with anything we were trying to do here. So mystery impl, oh, so it should have said mystery impl extends mystery. That's what it should have said, right? So the mystery impl provides the run method. The mystery main needs the run method. And to have a main object, you also need something that ultimately descends from app or explicitly provides a main method. So we had to plug these together. And here, the way I like to structure these kinds of building blocks is such that the executable main is just a one-liner where you say object my main extends and then the pieces you plug together. So like in process tree or in the iterator example or in your project 1A. Okay. And then here this is really just about running some tests where you invoke the run method. So you have to create instances where you invoke the run method with arguments, then look at the result and make sure that the result has the right elements. Okay, so kind of like the tests we have in the examples. So any questions, comments, concerns? I hope the review was helpful. You know, really, the goal is to build confidence in your understanding and ability to apply these concepts and techniques. I mean, that's really the key goal here. So let's move on to project 2A. And let's see. So let's switch over there to assignments. And let's take a quick look here. So as I mentioned, project 2A is tied to these nodes. So here's the section on these different building blocks. So 2A focuses on the variation concept, basically multiple implementations of the shape interface. So we're redoing your Android Shapes project minus the Android part in Scala. And the starting point is precisely this project 2A, the OO code. Let me look for that. All right, so here's the shapes code, so we'll look at that shortly. So here you should definitely start with the shapes OO skeleton, and then just basically fill in the blanks. In IntelliJ, for example, you can look at the to-do items conveniently. So there's a view and then the to-do items, or on the command line you can use something like grep. grep-r, and then that'll allow you to do that recursively. So that's very convenient. So let me just demonstrate that. Okay. All right, so here it is. So get into the git pull habit. Okay. Now, how do you do this on the command line? You can say grep-r, meaning recursive. Then you need the search term, and the grep utility is case sensitive. So If you want case insensitive, you can say -I also, meaning ignore case. And now you need a starting point. So if you use dot for the current directory, you would be looking everywhere, including the generated files, which is the target folder. So that would be would give you a lot of confusing output. So the idea is to do this just in the src folder. So it comes up with these places. So that gives you the starting points to look for. But again, in IntelliJ you can just say view to do, and then it'll just give you a little window with the same kinds of results, and then you can navigate there conveniently. So the idea is to, oh yeah, it says right there. So view tool windows to do. Right now, if I say SBT test, so the code compiles, but the tests, some of them fail, right? So that's your starting point. This is actually a false alarm. So this was from last Tuesday when we had to squeeze in a talk. Okay, so right now there are only 2 tests and they both failed. And let's see, what you will need to do is comment back in some of the tests that are commented out, complete the missing classes, etc. So let's look at the order in which we'll want to do this. In fact, let's take a look at the code, and let's start by looking at the shapes. Okay, so in the Android example, there might have been a few more shape classes actually fleshed out. So how do we know which shape classes are supposed to be there? We can start by looking at the tests actually. So let's do that. And we're going to back up and go to the tests. And we'll start looking at the fixtures. And the reason that the code compiles already is that a lot of stuff is commented out. So once you comment things back in, it'll stop compiling. So that's why I would do that gradually. So what I would recommend is the first thing is reintroduce an ellipse, which is similar to the circle in the corresponding Android project, but it has an A and a B, right? So circle has just one radius. The ellipse has the 2 half axes, okay, A and B. So once you have the ellipse, you can start defining some of those things, and then you also need a group, right? So group and location, those are familiar from the Android project, and that's basically it. So this one doesn't, it's a little simpler. It doesn't have a polygon, which is a little more complex. So, okay, so first step would be basically to define ellipse and group and comment the various fixtures back in, and then those still pass. I mean, they should compile, right? Then, what you'll want to do is, well, okay, so let's stay here for a second, right? So, add those missing case classes from the fixtures, and then make sure you have validity checking. So, it's like an assertion, or in Scala, you would write argument checking typically using a require, like here. And for example, when you define a location node, you need to pass it the x and y of the location that this represents. And then you have a child of type shape, and you want to make sure that that's non-null, right? So that's basically a constructor argument check here. Does that make sense? So you want to have similar things in your ellipse, and well, in ellipse you really won't need a requirement check because ellipse is going to look very similar to rectangle. But in group, you have 0 or more children, or maybe 1 or more. You might not want a group with 0 children, so it depends on certain decisions you make. But you shouldn't have any null children, so you need validity checking for those children also. Any questions so far about this? To clarify, this is basically equivalent to what you would have done in Java or C# or so, where you have a common interface for the shapes, so that's in Scala just a trait. And then you have classes that implement that interface. So it's a 2-layer hierarchy. And you might wonder, what's this business with these case classes? So Scala classes are basically like Java classes, but case classes are a new thing. What are case classes? Well, case classes, you probably remember from Java that when you define a class that represents some kind of like a value object or so, let's say a temperature value or a point or something. What are the things you have to make sure to include in your class definition, typically, to make those, the instances of those classes work, let's say, in common situations like putting them into a set or things like that? What are methods you typically need to implement? Constructor is certainly one. Yep. Exactly, those kinds of things. Like the standard methods that every Java object has, but the way they're predefined in the object class won't work as intended, right? So the equals method, how does the predefined equals method work in Java? What does it do? That's exactly right. So it checks whether the two objects are at the same location, which really means are we looking at the same object or at two different objects, right? That's how the default equals method works, and that's almost always not what you want. Like when you want a temperature value, you care, is it 23 or 24, as opposed to, is it this 23 over here or that 23 over there, right? So you need to redefine your own, or you need to override the default inherited equality method using your own that looks specifically at the instance variables of your object. So that's a typical process. So the typical methods you override are equals, then the hash code should be consistent with that, then the toString, you want something that prints something that at least is informative as opposed to object at some kind of hexadecimal location, and those are the minimum methods you typically override. If you want the things to be part of some kind of ordering, you also have to implement comparator and then implement a compare to method. Does all of this sound familiar? Right, so what does a case class do then? A case class basically does that for you, not the comparator part, but the equals method and toString and those kinds of things in a meaningful way. So what you can do is you can try this out. So we'll do SBT console quick, which brings up a Scala REPL without trying to compile your actual code here in the project. So you can just kind of play around with a REPL, or if you have the Scala package itself installed, you can just say Scala. But I usually like to have just SBT, which is just the minimum. So what I can do is, for example, paste this rectangle class, and I'm just going to do it without that shape trait, so just to play around with that a little bit. So it defines this, and now we can say also with a case class you don't have to say new. You could say new, but you don't need to. So I can just say rectangle 3,4, and it tells me, okay, I got a rectangle 3,4. Now, oops, that's that thing I got to set on this computer. So there's a bug in somehow in SBT. So let's define another rectangle of size 3 and 4. So now I have res 0 and res 1, and in Scala, so these are two different objects because I created them differently. In Scala, double equals is back to what you would hope it should be, which is comparing equality based on the actual instance variables in the case class. So this will say true. And then there's an identity method, which I think is EQ. I rarely use this. Oh, okay, this doesn't work. Forget it. Res 0 dot EQ, res 1. And this one says false. Okay. So the things are renamed compared to Java, but you're automatically getting a meaningful equality, which is uniformly, regardless of the type, expressed as a double equals. Okay, so the double equals is what in Java would be the equals method for object types. And if you really need object identity, it's this EQ. And that's why this one says false. Okay. The other thing that case classes give you, and this is language design issue, is so-called pattern matching. What does that mean? If you're not familiar with pattern matching, that's actually highly valuable to take a look at. And for that, we're going to look at this initial version of the bounding box method here. Let's see, so this is just the shapes. So bounding box is an object that is going to define this apply method, and there are going to be cases for each kind of shape that we might be seeing. What kind of technique did you use in the Android example to implement these kinds of behaviors? There's a particular design pattern that we used for that. Does anyone remember that? Where we had to say, well, if it's a circle, we do one thing. If it's a rectangle, we do something else. Visitor. Right, so switch is more of a, there are languages that have a switch construct, right? So C has a switch construct, and I think Java has one also. So that's for making a kind of case distinction like that. But that works, to my knowledge, only if the discriminant, meaning the value that you're looking at to make the case distinction, is something like some kind of basic value. Is that correct? Whereas here we want to make a case distinction based on objects. So A common technique is this visitor pattern where we say, okay, shapes have an accept method, and the purpose of the accept method is so you can pass an object representing the behavior with this case distinction, and that object is the visitor. So here we're using an equivalent technique, but we don't have to use the visitor pattern. We can, because we have a convenient, kind of a more advanced style of the switch statement, we can use that here and use pattern matching directly. So let me pull up a guiding example that will help you get up to speed with that technique and apply it to your project 2A. And that guiding example, it might not be mentioned here, so that's why it's particularly important to be aware of this. And we will go just back to the organization here and look at which ones might be useful. And it happens to be this expressions example. Okay. So in the expressions example, you have, as opposed to case classes representing shapes, you have case classes representing parts of an expression, such as numeric values and operators like plus, minus, and so on. So ignore the parser stuff. Look just at AST. So there is an expression trait, and you might have an expression like 3 plus 4. So 3 would be a constant instance representing the value 3. And then you would have, let's say, a plus, and then the left and the right would be constants 3 and 4, for example. So if you look at that, so your definition of your shapes is going to be similar to this, right? I mean, here you have more, but they're generally simpler. They're fixed numbers of children, whereas we will just have, so we already have rectangle and location, and we need to add ellipse and group, right? That we agreed on. But then the style of defining the behaviors is going to be very similar. So this is an example of pattern matching here. So there's the match case construct, which is like this enhanced switch that you were thinking of. So this represents the visitor, basically. Any of these kinds of methods represent something that you would have represented as a visitor in Java, but these are more direct representations of the same things. Okay, so what do we mean by pattern matching? So we get, and let's look at some of the fixtures. There should be fixtures in probably the test section. Okay, so there are some fixtures. Okay, so for example, so they're similar to the kinds of shapes that we built, right? So this expression represents an expression that in infix notation you would have written like this, right? So you have a div at the very top that corresponds to this one, which is the kind of outermost operation. Then you have the 5 as the second argument of the div, and then to the left of the div you have this parenthesized expression which has at its top a minus, so that's the direct child of the div, right? So it's kind of represented hierarchically as a tree. All right? So equivalent, these are all equivalent things like shapes, org charts, expressions. So they're equivalent in terms of the hierarchy structure. Okay. So now the behavior, the pattern matching, when you look at something like size, okay. Let's say you pass in this kind of complex expression. So that's your argument E, your incoming argument E. Okay. So then it'll look at E and figure out which of these applies to it, and then it'll it'll basically, so let's look at that side by side. That's going to make more sense. I'm going to duplicate this. And then pull this out over here. Okay. So suppose we apply the size behavior to complex 1. Okay. So we're sticking complex 1 in as argument E, and then it'll say E match, and then which of these does it match? Well, the root node is a div. So we'll go into the div branch, and then it'll say 1 plus size of L plus size of R. But what are L and R? So it basically matches the pattern to the concrete values. So it's like a way of breaking something up and at the same time associating these names with pieces of the structure you're breaking up. Okay, so here the L, the L up there, so where it says div LR, the L becomes the minus subtree, and the R becomes this constant subtree, which happens to be just a leaf. Does that make sense? So then, yep.
With this L and R division, you can only use 2 subtrees then if you want to do complex strings and more than 2, let's say, mathematical operations. You have to keep splitting it into 2 subtrees.
Right. So the way this example is written, every kind of operator has exactly 2 sub-expressions. So it won't have, let's say, 3 plus 4 plus 5, where you might have a plus with multiple children, where you're adding all of those. So this is only 2 at a time. But in the shapes, the group has 0 or more, right? You could have applied that technique here to the expressions also, right? So, okay, so then the point is, then in the visitor approach, what you would write here is you would have, the visitor would have a name, right? Or it would be this visitor, the current visitor. And then you would have had to say, you would have written, instead of directly just saying size, does anyone remember what you would have written in the visitor style? So for this line, like especially what's here. Here we're just invoking the current behavior recursively on the subtrees, right? How would we have written this in the visitor pattern? So you can probably just check your code, but does anyone remember? It would be a little more complicated, right? It wouldn't be directly. So you would say L dot accept. Does that ring a bell? And then you pass the visitor itself, right? And that's how you make that recursive call, but it really just represents a recursive call of that same behavior, applying that behavior to the subtree. So this is all a little simpler, right? But it benefits from the ability to do this pattern matching, which is this technique that allows, first of all, making the case distinction at the same time as then choosing the branch and then applying, matching, let's say, a pattern to the actual argument, and in that process assigning names or binding variables to pieces of the argument that correspond structurally. Okay, so in using pattern matching, you can write these kinds of things very, very concisely and naturally. Otherwise, you could still write those things, but you would have to kind of access the instance variables by using the dot notation to access those variables, like you'd be used to in Java. So that's also possible, but pattern matching using match case is the recommended way. All right, so I'm going to terminate this recording in an orderly fashion now, and we will see each other in on Thursday or during office hours. So have a great rest of the day.